Good afternoon, everybody. So my name is Kim Song Tan. I'm working with the Malaysian Rubber Board, which is a government agency of Malaysia. And we bought the AFM machine a couple years ago. And since then, we use it a lot in our R&D activities. Yeah? So today, I'm going to present part of the R&D findings using the AFM as a main tools. So the title for today's presentation is the studies of natural rubber-based materials using AFM technique. Right. So first of all, I will share a little bit about the basic concept of atomic force microscopy and the materials that we are interested in. And I will also share with you the preparation method for the samples that we made. And one of the samples actually not from us, but is actually from the industry. And there are some AFM modes that we use in the studies. So mainly it's for topography, but we also do some mechanical property testing. And one of them that we used conductive material in our samples, so we use the electrical modes. Yeah. And after that, of course, I will share with you some of the results, and of course, covering the topography of the samples that we analyze, and some of the physical properties. Yeah. Right. So as you all may have known, the AFM concept is a rather simple concept. If you heard about the a blind man and an elephant story, then you could have imagined that the AFM is actually a touching concept where there's a cantilever that is touching a tiny spot on your sample, and that sends the the signal to the controller and then to the recorder and to tell you the information on that spot itself. But of course, the spot is really tiny. It could be in nanometer, picometer kind of spot size. Yeah, the more spot size you have, the more spot that you touch using the cantilever, the better the resolution of your image. Yeah, it's actually a scanning probe microscope. It's just like the SEM. So you will scan from one left to right, then right to left, and that kind of the area that you are interested in. Typically, we go for a few microns up to for big sample like semiconductor. It might gone to like 100 microns. Yeah, but that is for ultra flaked, very flat surface. But for rubber samples, usually the flatness is not that high as compared to the silicon industry, or like the wafer or whatever. So we don't go for very high area scanning. Typically 5 to 10 microns is the maximum for us. Yeah. So since the concept of touching at certain at every point the cantilever is touched, so every information about that particular point is recorded. Yeah, so that particular information can be converted into mechanical properties. Yeah, such as how hard or how soft that spot is, whether that spot is sticky or not sticky. Yeah, something like that. Okay, or even whether that spot is a conductive or not conductive, thermally or electrically. Yeah, so all this information is available after one touch of that particular spot. Okay, by combining all these spots that being touched by the cantilever, yeah, you will be able to present it in a micrograph to show you whether whether it's topography or whether it's mechanical properties or electrical properties. Right. So of course, the materials that we are interested in is natural rubber base, because Malaysian Rubber Board is a R&D institution, and we do also natural rubber research. Um, the aim of our company is actually to support the rubber industry, particularly in Malaysia, but we also support the whole wide world. Yeah, if people have problem in the natural rubber, either the growing side or upstream, or the midstream, which is the processing part, or even the downstream, which is the rubber products. Yeah, we are able to offer uh, consultancy or collaboration kind of work like that. Yeah, in-house we have a lot of the R&D activity going on from time to time. Upstream, midstream, and downstream all covered. Yeah. So in today's presentation, I would focus mainly on the product size, which is the thin film of natural rubber, um, such as gloves. Yeah, and the additives that we are using in this study is, one of them is graphene. The graphene is the wonder material. Okay, everybody knows about it. So we are also trying to use it as a material, then hoping that the so-called the advantages in graphene will help the natural rubber film to gain extra um, uh, benefits, yeah, to gain extra strength, or spatial functionalities, such as electrical conductivity, something like that. Okay, and the other type is the surface coating. We don't use the graphene as a coating material, but we use another type of materials for coating. Okay, I will share with you later on. Okay, functionality of this, like I mentioned already. And the AFM modes that we are using here is the tapping modes, and also the electrical mode. Yeah. Okay. So for one of the samples that I mentioned just now is actually the coating onto this natural rubber glove. As you can see from the picture here, so this is a type of just surgical glove made of natural rubber latex. Yeah, and this particular sample I'm sharing with you here is actually a commercial sample given by industrial player in Malaysia. In the request, they would like us to look at the morphology or the topography, and also some of the mechanical properties, which I'm going to share with you later. Right. So in terms of topography, we can actually use that software to see it. Of course, the normal one will be 2D, and then we can actually see it in 3D. Yeah, and we can also see some physical properties and electrical properties, yeah, on the other type of sample. Okay, so this is 3D images that we normally see on AFM. Yeah, from the 3D images, it basically you can see how smooth your surface is, and then how uneven or how even your surface is. Yeah, we can see some the peak of the mountain, something like valleys, and the so-called the heights of it. Yeah, in this case, in these samples, it's around 200 plus and minus 200 nanometer. As for the sample on the right, it seems to be a little bit uh, flatter compared to the one on the left. Okay, never mind. I'll show you again later on. Right. So later I will show you some live using the AFM software in how we actually measure this. So this is the results that we got for this particular sample from the industry. And as you can see from this image, this is a 2D image, and you can see that this is a particle, big, huge particle here. Yeah. So these are actually um, foreign particles. Usually in the industrial, in the natural rubber latex industry, after they make the natural rubber gloves, they will need to have some powder to coat on the surface. to prevent the film or the glove to stick together. So these are the powder that actually applied to the surface. And from the other side here, you can see the surface with some coating. Yeah, here also you can see some coating. And if you draw a line across the image, you will be able to see a line profile like this. And then from the line profile, yeah, you can roughly estimate and calculate the how thick your coating is. In this particular case, the coating is around 100 to 120 nanometer according to the scales, yeah, on the left here. Right. Okay. So these are the comparison between topography here, the height, the Z height, and in 2D, and then the addition force on the surface and the addition energy. Addition energy and addition force, they are more or less the same, as you can see from these two images. So the bright color and the dark color are distributed accordingly, yeah, almost similar. But if you look at the height here and the addition force here, so if you compare these two together, you see that this particular big particles, yeah, is having a very dark spot here, yeah, big dark spot, and this particular one as well, yeah, compared to this one. And that tells you what these two area or these two spots are actually very low in addition force, okay, which means they are not the rubber material. Everybody knows that rubber is sticky, okay, so we need this kind of material to prevent them to stick together. So look at these other parts. You will be able to see that some are very, very bright. Yeah, some are somewhere in between. So it tells you that where are the very sticky part. And as you can compare the sticky part here, the very bright spot here actually refer to some of the lower part in between the coating material. So it tells you that the sticky one is the natural rubber, and the non-sticky one is the coating material, and the dark one, of course, is the foreign material here. Okay, so this is another one. Another sample, actually we tested two samples here, and this sample is better than the first sample. As you can see, if I cross a line, there's a line profile here, and this line profile shows that the thickness of the coating is around 100 nanometer as well. Yeah, 100 or 120, something like that. Okay, it's similar to the first image. Okay, so now let's go to if I can show you the software. Okay, this is a software we are using for the measurement just now. This is the 2D image, and 3D image is like this. You just click 3D, and then you can see here. Double click, you go back. It goes back to the 2D, and then you just drag. Yeah, drag the image. You can see wherever you like. Okay. In this particular sample, this black spot is probably this is actually the valley. As you can see from here, 3D image. It's valley. This is the height image. So okay, and if you go to the 2D image and draw a line here, you can move the line wherever you like. For example, let's go to this part. Okay, this part is somewhere in the center. Yeah, somewhere in the center here. You can see that this is the low. Okay, the lower part compared to the both side. Yeah, so which is around this area. Okay, and then you can actually measure the size. Yeah, compared to the scale here. So it's around 100 nanometer. Okay, and you can see the coating material very clearly. Let's see whether I can zoom in here for you. See, this is a coating material. Yeah, and then here is the natural rubber, as you can see just now with you. Let's see. Okay, let's put them together to see more clearly. Okay, on the left here is the height or the topography, and on the right here the addition energy. And some people feel that the color is not clear, but we can actually change this into different type of color tone. Then see, compare this one and this one. Okay, let's take this spot in the middle. Okay, you can see that the height one is referring to this, which is the low addition energy compared to this. Yeah, so it's very clear that this is the coating material, and this is higher than the natural rubber. In this case, on the left, the blue is natural rubber, and in this case, the blues are the coating material. It's very clear, and you can see where your coating material is and how good they cover the surface. Yeah, and the distribution of the coating material, whether they are good or not good, something like that. There are a lot of information you can get. Right, you can even calculate the roughness here, but we don't do. Yeah, let's go back to the presentation. Right, where we are just now. All right, so okay, this is the commercial sample. Let's go back to our in-house nano composite using graphene and natural rubber latex. Yeah, so how we do this, how we prepare this material? Of course, we have natural rubber latex. Yeah, and also we bought some graphene suspension. So we add these two together at certain amount, certain percentage, and then we use high-speed stirrer, or we call it high-speed mixer, and then we mix that for 1 hour, and we cast the film into a mold and let it dry under the room temperature for overnight. Sometimes your film is too thick; it might take 1 more day. Yeah. Um, and both sides of the firm were analyzed in this case because we see some difference in the two surfaces. And the main mode that we use in this study is the electrical mode. Okay, I will show you how we prepare sample. Okay, in order to study the electrical properties, you have to make the surface conductive to connect both the sparks with the sample with some silver paint. Yeah. Okay, so I'll show you some of the results. Yeah. Okay, first is the structure of the surface. Let's see. Um, the one this on the left, yeah, is the surface that's facing up during the casting process. So as you can see that you can see some of these particles are about 1 micron in diameter. So clearly that these are the natural rubber latex particles. Yeah. So this is a 3D image. So on the other side, the bottom side, which is in contact with the glass mold, we use a glass mold. So the surface is totally different, as you can see here. The topography, look at the 3D, is totally different, structure. So interestingly, their physical property also different. Let's see. Yeah. Okay. Both sides have distinctive surface morphology. 1 micron particle are the latex particle, and the undulating surface on the conductive side. Yeah. Okay. Electrical properties. The surface on above, yeah, the film that we made is like this. There's no conductivity. Oh, yeah, it's not recorded anything. Even up to pico m, as you can see on the top left here, up to pico m, there's no conductivity. But on the right here, which is the bottom part of the film, then we can see some bright spot like this. Okay, these bright spots, they are conductive. And the value in this case is at around nano m scale. As you compare these two, the scale, pico m and nano m, they're different by 1,000, yeah, the order of 3. So it is quite clear that on the surface on the top, it is not conductive. The surface at the bottom, it is conductive. Okay. So this is what I shared just now. Okay. And what about the face imaging? What face imaging can tell you? Yeah. On the left here again, this is the non-conductive side, the topography, and this is the face imaging. Yeah. So as you compare these two, you can see that the particle here, let's say take this one as example, a reference point, and then you can refer to this one. Bright here, white, and here dark. But outside the darker part, you can see some bright spots. Yeah. So it shows that there are some material that is different, slightly different in phase. So showing in this particular sample, yeah, particular surface. But we are not sure what they are. Yeah. There is error in the measurement. But we are pretty sure if you look at the bottom part of the film, like this, yeah, just now I show you this image already, the 2D one, and this is the conductive side. This is the so-called phase imaging as well, and you can see really, you can see some very dark black color, yeah, area, and these areas actually corresponding to this area, which is the lower part. If you can see, okay, the 3D image here is the valley of that particular surface that we analyze. And not only that, on the left side here, you can still see some black color stuff here. So these are actually a totally different material as compared to rubber. Yeah. So we can actually confidently say that there are a lot of different non-rubber material in this particular area, and the conductivity shows that this material must be graphene. Actually, graphene is very high in electrical conductivity. Yeah. Okay. So what are the phase imaging can tell you? The phase imaging can tell you elasticity. Yeah. Different material they have different elasticity, addition as well, and also friction. Yeah. And we see the good contrast in the second one, the bottom one. Yeah. The bottom surface, and clearly shows that there are two different material uh, on the surface, and we can also see the agglomeration. Yeah, agglomeration happens in this material. So big dark black area here. Okay, so they are graphene agglomerates. They are electrically conductive. So as a conclusion, AFM, atomic force microscopy, is a very versatile tools, and it's very easy to use. As I mentioned just now, you just prepare your sample and put it in, and then you can run straight away. And at one run, you can get a lot of information, yeah, including the surface structure and physical properties, and also some of the other properties such as electrical conductivity, something like that. You can also do thermal conductivity if you want. Yeah, you can also do some your wet sample. Yeah, we do have that modes, but we haven't tried yet. Okay, and of course the thickness of the coating is the most important thing for industrial people at the moment, because they want to know how much material is being coated on the products. Yeah, so can't they coat 50 nanometer or 100 nanometer? They don't want to coat microns of material there. That's all dollar and cents. Yeah, they want their material to be coated well, coated but thin enough to save in cost. And also addition properties will tell you whether they are rubber or not rubber or other materials. Yeah. Okay. So we also conclude that the sample that provided by the industrial, um, the coverage of that coating material is not 100%, but they are quite well distributed on the surface. Yeah. So the graphene nanocomposite, rubber graphene nanocomposite, um, I think the most excited part is we actually measured some conductivity. We also actually use another device to measure the surface conductivity, and it does conduct electric on the surface. And people do not know why one side cannot conduct electric and one side can. Then under AFM, you will see why, because it has a agglomeration at the bottom. So probably is the sedimentation process happen during the drying process. Yeah, because casting takes 1 day to 2 days. If the film is take 2 3 days sometimes, so that times allow for a small movement in molecular level. Yeah, the graphene might migrate to the bottom of the surface. Yeah. So, and again, the phase analysis can identify different material on the surface. So with that, I thank for your kind attention. Thank you very much.